Swayam Prabha. Digital India. Educated India.
So I have only 10-15 more minutes because we are now talking interesting things about collective effect of particles, and I'm pretty sure some of you are using Richardson-Zaki kind of relation, or you probably are using Gidaspo or some correlation. Okay. Yes.
So one of these Richardson-Zaki correlation comes into picture when we carry out the terminal settling velocities of a bunch of particles settling together.
Yeah.
So there this correction also comes in terms of point fraction.
Absolutely. In fact, I'm glad that you asked. Richardson-Zaki relation is derived by average settling velocity. When we put this in here, we're just sort of working backwards and say what drag change would give you the experimentally observed settling velocity. So in other words, it's a reverse engineering of a little bit to come up with this kind of a correction. Okay. He asked a fabulous question, and you are following it up. See, this drag law is a very funny business. First of all, drag laws are all over the place. And the way we use them often is not the way they are supposed to be used. So, not that I'm trying to find faults with anybody's work, but it's just the nature of the business is so hard that you pray God and use the best available. So in other words, many times we end up using it in ways that they were not derived, and I will explain that in a minute. Say for example, we had a discussion. So when is this formula valid? What is U0 when you have a freely moving random particle? A fabulous question. Is an excellent question because it's not obvious. What is U0? When you have a stationary random or stationary structured array, I can see what it is. It is you go inside your bed and you average a fluid velocity everywhere. That's your U0. Okay. Can we 1 minute? I will finish and then I will take your question. Okay. So I myself didn't appreciate that. His question made me think, and I think it's a fair thing. Bachelor's U0, please go and read that paper. I believe what he means is you average all the fluid velocity as the particles are falling down. In the gaps there is fluid. You calculate the average velocity, which will go up, right? When the particles are coming down, on average fluid has to go up, okay? And the average particle settling velocity, everybody is settling differently at any instance. You know, you take a picture, one may go a little faster, another may, there is fluctuation. It's pseudo turbulence, by the way, because if the particles Reynolds numbers are not, it is not anybody steering the pot, it's just the particles are steering themselves in a way, okay? So I think U0 really means take the average fluid velocity minus average particle velocity. Now, so we know what this formula is for, or at least what goes in there, that phi d is also average volume fraction because you may have little clusters here and there, okay? But actually in Bachelor's analysis, he has sort of, he doesn't have any micro scale structure. When you do an experiment, you might find some clusters here and there. That's a whole different story. But anyway, given phi d and given U0, that f is not for an individual particle, it's an average. So you put in average information, you get average out. And you think for a minute, when you do an Euler-Lagrange simulation, how do we use it? We calculate the relative velocity of the individual particle. We never ask for when you apply the drag force on a particle, we only look at the relative velocity of that particle, and we apply this formula to that particle for the drag force. So we are doing two errors. One, input is not average and output is not average. You apply it for individual case. But that's how we use it. So I will stop there. So in other words, we're not necessarily using these drag formulas often, how they were derived. And you talk about settling velocity. If you go here, this formula was derived for settling case. In free settling case, volume fraction could vary here and there. And Richards and Zaki, he didn't care for all those things. They said on average over all the particles. Here is the average volume fraction. Here is the settling velocity, average settling velocity, which translates to average force. But we again use this kind of formula for individual particles. Okay, so whether that is correct or not, I can't say. Certainly, it's not kosher. It's not perfect, but this is how we use it. Okay, I just wanted to sensitize you for that. Yeah. He is patiently waiting. I said 1 minute, and he has been waiting for 5 minutes. Go ahead.
Okay, so like if I remember correctly, this is for the settling, right? All the particles are
Yeah,
settling at
yeah.
the same time. So
This picture is, by the way, is bad. So it's too much large volume. So he considered a dilute system falling down. Yeah.
so that means from that expression I can see that even if the individual settling velocity is more than the average settling velocity, like the
No, less than.
is less than the individual particle settling.
Yeah, it is less because the drag has increased.
Yeah.
So this is called hindered settling. By the way, that's a great thing. So this is basically hindered settling. So in other words, a single particle will settle.
Yeah, but at the same time, if I consider a cloud of particles like yesterday or the yesterday, that it will fall
Much faster.
much faster.
Yeah.
So
Why is it not happening? Either
that's because of particle-particle interaction.
no, it is because of inhomogeneity. This blob has particles, this side has no particles, this side is no particles. So in other words, you have a blob whose weight is little more than the surrounding fluid. So it's sort of like dropping a bigger ball of heavier ball, and it's going to drop fast. What Batchelor considered is homogeneous layer. Nowhere else it's heavier. Everybody had particles, so nobody can run faster. So in that case, you only have hindered settling. So particle settling is nothing but easy. Okay. So in other words, he is only considering a homogeneous medium settling down. Okay, there is no body sort of leading. Now, but in reality, this is not what's going to happen. They fall down, but at the same time, there may be some instabilities, and you may have blobs of particles that may fall down faster. So the way to think of this is, you have a tank where you stirred everything. So it's not like a layer of particles at the top falling. The whole tank has particles and everybody is falling. So there is not going to be any inhomogeneity. Okay. Make sense?
So particle-particle interaction is nothing to do with it. I mean,
No, particle-particle interaction is the reason for this. Particle-particle interaction, that's why it's called hindered settling, is the Stokes flow created by each particle affects the drag on the other particles, and therefore collectively each particle is slowing down everybody else a little bit. Okay, that's the way to interpret this. Yeah.
and this is like summation of all pairwise interactions.
Actually, pairwise interaction will not give you this answer, okay? Because since it's Stokes flow, the interaction is n-body interaction. So that's the problem with Stokes flow. So it's a difficult derivation. I mean, derivation not the actual step, the conceptually the steps he took to get this answer is pretty challenging. Okay, maybe you could read what I have written, but if that's not clear enough, you can read Batchelor's original paper and there may be other people expanding on that. But it is not pairwise. It's a good question. I don't know the answer. I don't remember whether it's pairwise interaction will give you the answer or it is more than pairwise interaction. I must admit I don't remember the details. Okay. Yeah.
Sir, with respect to this formula, like we were talking about how we would apply to the Euler-Lagrangian.
Mhm.
So when we're considering an Euler-Eulerian simulation, would you say that this is appropriate, more appropriate?
That's a very good model then. Yes, you're right. So this is the kind of formula maybe derived for Euler, because in an Euler you have a cell, you have average fluid velocity, you have average particle velocity, and therefore you have every right to use this, and then you can use it as average. That's an excellent point. So these drag laws are perhaps better suited for Euler simulations. Yeah. Then Euler-Lagrange simulation. Yeah, that's actually a nice point. Yeah. Any other questions? Okay. So I want to show this result. This is simulations by a lot of people. They took random array like this. So this is the problem they studied. While Saffman did this problem for low Reynolds number, people now are doing the same simulation for varying volume fraction, varying average Reynolds number. Okay, and here you can see Bierstraw, Tennety, Zaidi, and my student also did. So what they did was varying Reynolds number, and this is I don't remember, maybe I'm sorry, maybe 5% volume fraction, 10% volume fraction, or 20% volume fraction. I mean, take that with a pinch of salt. So you understand the three figures are for three different volume fractions as a function of Reynolds number. And this is what you would have predicted if there was only one particle. That's the drag force. Increase in drag is what you will call hindered. If it is settling, you would call it hindered settling. So here these are not settling particles, they are stationary particles. The point is that drag increases substantially because of, in this case I can assure you this is not pairwise interaction. Pairwise interaction will give you, we have tried that, it will give you maybe some approximate answer, but this is n-body interaction between the particles. So the first point is that yes, there is substantial, so you have to take into account volume fraction, like a Richardson-Zaki correlation or something you have to use to do this. But I want you to think about, look, these guys don't seem to agree. That's the best status of, I mean, this difference is substantial. In other words, there are 5 different direct numerical simulation giving 5 different answers. What do you make out of it? These are direct numerical simulations. Okay, so this is an unanswered question. It's bothersome to me, but that's the way we are right now. I mean, there is I mean, people may say, okay, I capture a big jump from individual particle, but still really the jury is out there why there is such large difference. So one thought may be, everybody says that it is uniform random distribution, but one question maybe, is all uniform distributions the same? Maybe some a little bit more clustered than others. Maybe it is the box is too small, too few particles. Maybe numerical resolution is not good enough. But it would be very nice if somebody can nail down this is the answer. Okay, so there should be only one answer because this is average, but we don't know what that thing is. We have been using Tanety's results, but we also lately I find that they use too small a box, too few particles, etc. So I just wanted to leave it there. So there is some room for some really high quality work to be done. This is Tanety's formula. Now remember, this correction is not a function of Reynolds number, but it's now a correction of Reynolds number and volume fraction. This has been derived for stationary particles, so be careful. Okay, this is true for stationary particle. The Reynolds number is the average Reynolds number. Okay, since the particles aren't moving, particles don't have a velocity, so this is based on average velocity, and the phi is average volume fraction, and this is good for average drag. Therefore, this is good for Euler, but everybody uses it for Euler-Lagrange, and they apply it for individual particles. I wrote recently a paper, I think 2021, just myself, I don't have any co-author, I just did that work. There I compared what happens if you use this for individual particles. Do I get the average drag? Okay, that's an interesting question though. I tried that, very similar to the question that he asked. There is a little different. So in other words, if you apply this for every particle and then average, would the average be the right average? Okay, it doesn't, but the error is maybe 5% or something like that. So if you use this in Euler-Lagrange, it's not you're going to totally be wrong, but there is some error involved. Okay, but you may say, I don't care, because this formula itself is great suspect, because there is so much uncertainty. What's wrong if I do a 5% error? There is nothing wrong. If somebody questions your drag law, you go tell them that, tell me a reliable drag, then I will use it. Okay, so there is a lot of uncertainty in there. Okay, don't quote my name though. Okay, don't tell that Balachandra said that. You risk your name. Okay. I just have 5 more minutes of presentation. I just wanted to go back to the thing that we did. This is the same thing that produced this curve, the average drag. One of our line is in here, and we don't agree with others either. Okay, we think that our answer is the best, but we don't know. So here. So what we did was we take a random array like this and put a pressure gradient and push the flow, and our pairwise interaction came out of this. You see all those red particles have very big drag and the blue particles have very low drag, and this is what I was talking about. We did DNS. It's a little expensive simulation, maybe 30 for 50 million grid points, etc. Immerse boundary method. But then it's interesting that if this was one finite volume cell and you have all these particles in there in a Euler-Lagrange simulation, we would end up giving all of them the same drag. So that's something that I want you to think about. So this was in 2017. Since that time we have been working on how do we create models where drag could be calculated based on neighbors. Okay, so we have a bunch of papers. If anybody is interested, you can follow up. Right now they are not in a form that's user friendly in the sense that, but you know, that's going back to what we discussed on Tuesday. Maybe machine learning or other things may do a better job. So the thing is that if every particle, imagine a situation for every particle, you give it the average Reynolds number, average volume fraction, but you also tell where its 5 nearest neighbors are or 10 nearest neighbors are, because you anyway have them. Could you predict a better drag? That's the kind of question. But anyway, so this is the quantitative information. So as a function of this is x direction. So I listed all the particles and their drag, f drag is plotted here, and this is what I'm saying. The red line is average. This particle is almost twice the drag. This guy is really low drag. And we did a lot of work trying to figure out what really matters. Not only this, you know, the most interesting thing is that each of these particles has substantial side forces. Okay, that side force is not due to the mean flow. It's because your neighbors sort of redirecting the flow. Look at this lift coefficient is 30% of drag, and many times we don't even put it in our code, okay, because the average is 0. So we apply that the average lift. there is no lift. So this may be sometimes damaging, because imagine you have a channel and you have a bunch of particles and flow comes. What this says is that neighbor-neighbor interaction will have a lot of side forces. Now you will have dispersion due to lateral dispersal due to that, and the streamwise force variation will increase the streamwise dispersal of that cloud. So if you want to capture those real useful quantities, you really have to, we have to do a better job. And this picture just say the flow is coming into the board. As you can see, the left particle is going to have low drag, and the right particle, is in the channel. So we were able to say why this guy is so large, why this guy is low, etc. But then turning it into a reliable model is quite a challenge. But one thing we said was, maybe you don't need to know exactly what the particle force is. We said that we took all these particles drag, it looks like a Gaussian. We took all the particles lift force, we get a Gaussian. So we said that maybe you shouldn't use Richardson-Zaki relation in a deterministic way. You use Richardson-Zaki to get the average force, but then maybe, and also by the way, the sigma, the RMS in both cases, or at least in the drag, is always reliably about 15 to 20%. So we came up with a very simple stochastic drag model. We say that you take your Richardson-Zag model and add a 15% randomness in every direction, and you add it. Maybe you might capture the dispersal better. It may not be the right thing. You may end up giving more drag to one that really deserves to be a low drag, but you may end up giving it higher drag by mistake, because we are just playing Russian roulette here, okay? But at least it might capture something better. So if you can't give precise drag to all the particles, the next best is, my recommendation would be for those who are using a real Euler-Lagrange kind of approach, okay? Now for Euler, going back to your question, on average you are doing a very good job, right? But you may have to have some such thing to disperse the particles, otherwise you will miss out this. The fact that particles have different forces will make them move differently. So if particles are moving differently, that will give rise to dispersal of particles, okay? So how to do this in Euler simulation, I'm not quite sure, okay? So drag models as a function of Reynolds number and phi are, I shouldn't say emerging, it has been there for a long time, Richardson-Zaki and kind of Gedaspo and other people, and new generation of models are emerging, and I highly recommend you to think about stochastic modeling, which means you add a stochastic component to if you're tracking particles, and combine that with the Langevin equation that we talked about this model, okay? Now, yeah, so that's something that you might want to think about. And I said there is still some uncertainty even about mean drag. And forces of individual particles are substantially different, and I talked about stochastic model. I will stop there for today, okay? Any questions on that? Yes?
This is related question. So the Langevin model, that is also for dispersion, right?
Yeah. I'm glad you asked. This you need even if you are doing DNS in some sense. You remember, excellent question. What we talked about in morning was releasing, I talked about releasing a cloud of particles, but the right way to describe it, you release one particle at a time in that little volume and watch where they go. That's the right way of thinking, because I didn't do any particle-particle interaction. I was only talking about one particle, if it were to move in turbulence, how does it disperse? You understand? So there was no pairwise or any kind of interaction there. Morning lecture, particle-particle interaction, we just started this afternoon. Till that time, we were only dealing with. So their Langevin model is when you did not take into account turbulence fully, even at the level of one particle. Now what I'm saying is that I'm adding more complexity. Let's say your DNS you're doing, and you're doing Euler-Lagrange simulation, you're tracking a pack of particles. It's a DNS, so your turbulence is fully there. And you go to one finite volume cell, and there are 5 particles in there. You have a turbulent resolved flow, you have the excellent fluid velocity. All I am saying is those 5 particles now will have different forces because they are jockeying, pushing each other. That is entirely new physics which we never talked about before. So you have to do the stochastic model for the mean flow. And if you are now, so in DNS you add the stochastic force. If you are doing Rand's model or some such thing, then you have to take care of the missing turbulence and particle-particle interactions. You have to do both of them.
If you're doing DNS, like in particles also.
No, I'm resolved particles.
In DNS, we resolve the particles. So in
No. My DNS, what I was talking about is only turbulence is resolved. The particles are very small, so sort of like a pseudo DNS. If you're resolving the particles, now I mean, none of this is an issue. Okay, but resolved particle simulation, you can simulate maybe 1,000 or 10,000. I mean, what good it is. Okay, I mean, it's good we do those things to learn something and create models, but for practical problems, you have to simulate many more complex turbulent flows and so on and so forth. So the question is, if you do a turbulence resolved simulation, but particles are tiny, you still are missing particle-particle interaction because you took them to be point particles. And that's the thing that I was talking about. But this morning what I was talking about, no particle-particle interaction. You could drop one particle at a time. Okay, we're talking about how to take care of Rands where you miss the turbulence. Okay, 2 different problems. Okay.
So then the dispersive effect that needs to be added to any simulation, whatever we did using the stochastic modeling. So like, what is that exactly taking care of? The drag variation, that's what we're taking care of?
In the morning one or no? No. So what is dispersal? Dispersion is nothing but, if you have a crowd of people and they disperse, means why would they disperse? Because everybody has slightly different velocity. They are not, so a marching army will never disperse, right? It's just lockstep. So the question is, whenever particles have fluctuating velocity, they will disperse. And the fluctuating velocity because fluctuating force. This guy's force and that guy's force are slightly different. In the morning we talked about, if you did Rand simulation, you only have average velocity, but really behind the scene there was turbulence, and therefore we say, okay, if I took care of it, particles will have random velocities, and how that will contribute to dispersal. But today, right now what we are talking about is particle-particle, just by their positioning, may create slightly different forces on each other, and therefore each of them will move slightly differently, and there will be dispersal. The easiest way to see the dispersal is, you have a pack of particles, fluid is coming this way in that cell. I said that there is a significant lateral force. Some of them are pulled to the left, some to the right. So that pack will become bigger, right? Because it will swell. If you gave all of them the same force and they're all going to move downstream the same way, you miss that. So I'm saying, take Richardson-Zaki or whatever drag law that you have, you apply it, but add 15% fluctuation. Jiggle it a little bit. That might take care of your volume fraction effect. Now, don't quote me on the 15%. You have to look at the paper and see what it may be a function. As volume fraction goes to very low values, you don't need to add anything. But volume fraction increases, the fluctuation increases. So some stochastic model. Now this is not because of the missing turbulent, this is because of particle-particle interaction. Yes.
So there were two formula for forces. The one based on the volume fraction and the one based on the Reynolds number and volume fraction effect force.
Yeah.
So can we have a just summary of the differences between the two?
Question of what you like. I mean, these are two different models. Okay, this is the model based on stationary particles, particle resolved simulations. It's average. Okay, input is average volume fraction, average Reynolds number, average drag correction. Okay, this is by 1080. By the way, there are other guys who give formulas very similar to this. It all comes from this plot. Now this one is Richardson-Zaki kind of relation. Like you correctly pointed out, it was developed based on experimental empirical observations and curve fit of the experimental mean settling velocity. Okay. Now I'm not sure which is better. We have been using this, but sometimes this could do it better. I mean, yeah. I mean, you need to look a little bit more closely your application and how these formulas were derived, which is closer to your application and which you feel comfortable. Okay. The other thing is that to put these things and try and best thing if you have an experimental case, simplified, and you can validate and you might test, because they all have sensitivity, etc. Okay. But the main point is, no matter whether you use this one or this one, there is a stochastic component you might need if you want to capture. So that's one message that I want to leave.
Yeah, so in the morning, like you talked about the stochastic velocity gradient model for say your forms, different model. So the only restriction there, those particles with the subcolumn of
Yes, it is, but you could extend that to non-Kolmogorov particles also. See, these models, just like low Reynolds number models, they have been derived with some simplification, but nobody prevents you from using them to push the boundary of the model. If you don't have anything for a finite particle, what are you going to do? Okay, so I would say this: if you're tracking particles in Rand's model and the particles are of size 5 Kolmogorov scale, I say go use Langevin model still. It's okay.
like how different it is from the actual DNA. Let's see if I solve the same problem using like where I solve the velocity field using DNS and then track the particle, and the same thing using the Rand's or radius and then track the particle. Is it the similar?
Yeah, that comparison has been done. There is a lot of paper on Langevin models, and I certainly am not an expert in that. Okay, and you should check that, and they have done exact comparison what you're talking about. In fact, they improved the model. The Langevin model I wrote is extremely simple. There are much more complex Langevin models developed by Steve Pope, is one of the legend in this thing, and also Minier, M-I-N-I-E-R. Okay, he has written a lot of, and Delby. Okay, there are a lot of, and Professor Ahmadi. So there are a lot of people have studied exactly this. This is called continuous random walk problem, Langevin equation. So it goes by many names. So there's a literature, and they do exactly what you're saying. They do RANDs and add this model and DNS and compare. Does it do a good job? Okay, and they tweak and improve the model. So you want to take my lecture notes only as the starting point, but you want to look at, if you're looking at wall bounded flow, you want to check wall turbulence Langevin models. If you have, say, mixing layer, then there are people developed Langevin model for mixing layers and other free shear flows. So you want to go and do the literature survey and pick up a better, more appropriate Langevin model. And there they develop those better models by doing exactly what you're saying, is do a DNS, do a RANS or a LES, and ask the question, how can I get the DNS answer cheaply?
All these simulations are point particle simulation.
Point particle simulation.
So for the finite size particles, which is that
What do you, I mean, when you say finite size, if you still use drag law, it's a point particle. I don't fully understand what you mean by finite size. You either do fully resolved simulation, or then you don't need any of these things. But if you're going to do a drag law, whether the particle is sub-Kolmogorov or about Kolmogorov or slightly bigger than Kolmogorov, you have to rely upon some turbulence random fluctuation. You have to use Langevin model. But your question is relevant. If you read a paper and they developed a Langevin model for very tiny particles, is it still accurate when your particle gets bigger? Again, that question people have asked, and there may be some study, I am not 100% sure. So you could look into the literature. But the idea will be some modification for finite size for a Langevin model. But no matter what, you cannot escape from something like a Langevin model, because it is a very simple physics. It says I need to add random component. It must be correlated in time. It cannot be a random amplitude. It must have the right amplitude fluctuation, and you put them all in and you get the reasonable answer.
So in the stochastic model, you have shown that in the Richardson-Zaki model, you have added that to address the fluctuations, 15 to 20% of
Mean, that's right. It's a particle to particle variation. That one particle is higher, another particle is, we try to take care of it.
Yes, sir. And so what about the lift forces? That also was
It also, I showed you that it also follows a Gaussian. Its mean is 0. So some particle you will have to push it to the left, some particle to the right. Average will be 0, but you have to give random side forces. I don't know what so in other words, if you have a Gaussian, all you need is the mean and the spread. Then you can stochastically pick an answer to satisfy that distribution. The mean for lift is 0, mean for drag is maybe Richardson-Zaki or whatever it is. And the spread as a function of Reynolds number and volume fraction, it's in the paper. You can look at it. Yeah. All right. Thank you guys. Tomorrow I'll see you.